Hello, everyone. So, because time is strict 15 minutes, so I will just briefly introduce this session. In this session, we will have 4 presentations relating to the topic of signal interference. We will take a listen from the speakers about jamming and spoofing detections, footprint computations, radio interference level estimations, and about the characteristic of the ionospheric layer that may affect the quality of the GNSS signals. So that is for the content of these sessions. So to be start, I'd like to invite Dr. Nguyễn Đình Thuận for the first presentations about the jamming and spoofing detections and footprint calculations. Please keep in mind that we have about 13 minutes for each presentation, 1 or 2 minutes for 1 or 2 questions. And if you hear the sound from my computers, it means that the time is almost up. Okay? Thank you.
Thank you so much, Professor Lativing. Hello, everyone. I will continue my presentation about the GNSS and recent study on interference mitigation in Navis Center in Vietnam. I think you are here. We will wonder why today we will present a lot of things about the GNSS interference, because as you may know, now in Vietnam, due to the requirement for the public transport, the vehicle must equip the GNSS receiver for checking device. So that also raising the problem of the driver, the public vehicle driver. They're using the jammer for because they don't want the authority and government check their device. And also another problem in Vietnam now, so there are some people they're using the GNSS spoofer for changing the location of some people and in a specific area. That is the reason why in the conference we raised a lot of we mentioned a lot about the GNSS jamming and interference. So. Of course, nowadays the GNSS is already applied in the many sectors, such as you see, we use the CPS time for synchronize the power grid, also the bank, the transaction, and also we using the CPS time and position for for transportation and for the communication. So for the presentation, I will show you very short about the GNSS basics. And I will show you the point why the GNSS is a very vulnerable of the jamming and spoofing. And from there, I will give you some summary of the mitigation techniques applied on the GNSS threats. From there, I will show you the recent study of the jamming and spoofing mitigation, which are currently on research in Navis Center. As you may know, for the navigation actually we on the GNSS receiver we try to solve the solution based on the position of the 4 satellite, and also we solve the solution. We solve the equation to see the position of the user, and we already we can measure the procedure range based on the code phase or carrier phase, depend on the technique you use. And also we can calculate the satellite position based on the FM risk data transmits from the satellite and also the time. From there you can set up the equation and then we solve the equation using the Taylor expansion to see to get the solution. So we from the satellite, you may know the GPS satellite, we transmit on the mostly on the 3 bands, the L5, L2, and L1, which is the commonly used. And the propagation, the signal transmitted to the receiver. If we get directly the signal, we can get the highest quality. But due to the ionospherics, the signal is rejected, and also the signal maybe is due to the high buildings. We get the multipass that will raise the errors of the GNSS signal. And the GNSS signal is cannot pass through the high building, the objects. So is is the center of the city with a lot of the high buildings. The quality of the GNSS receiver is very low. First, the reception to calculate the time delay, we based on the the cost from the satellite and the cost at the receiver to calculate the time of propagation. To summarize the errors due to the transmission, including the satellite collapse, orbit collapse, and ionospheric delays, tropospheric delays, receiver noise, and multipass. The value may be changed depending on the condition. So to solve the resolving the errors, we have many techniques such as using the carrier phase. And you see, this is the image I want to show you. You see, although in this case we use the GNSS, the rover can can get the correction, but the correction in this case using the radio link, and the radio link and also the signal from satellite is not the the authentic message. This is very easy to the spoof or manipulate the signal. I will show you later. Also, using the S-bus, the satellite from the S-bus is not the authentic. It's not the authenticate message. This is quite very easy to manipulate. Also, the signal from if we using RTK. So next, I will show you how the GNSS receiver can measure can estimate the code delays. As you see, this one the red one is the code phase is from the satellite, and the blue one that is from receiver. And from the receiver, we will try to replicate, and we change the delay, and then we get the correction. If we find the blue one and the red one with the same delay, we get the highest spec here. That is the main techniques of the GNSS receiver. To summary, the signal processing chain of the GNSS receiver contains you can see the front end. The front end actually is just digitalize the signal from the satellite, and then with the acquisition and checking is using the FPGA or using the software receiver. It depends on the receiver. And now after the acquisition and checking, we can get the data bit recover. The data bit from the satellite is constructed here. Also here we get the delays. And then from the data bits here, we decode we can get the navigation message, and also combine with the delays from every satellite. Every satellite we can calculate the PVT computation. As you see, in the signal processing chain, they know the step for verify whether the signal is authenticate or not. Is authentic signal or not. That is the main problem. Yes. Okay. This is okay. I will not. So from on the step I already showed you that will raise a lot of the threats to the GNSS signal. First, it is the signal interference and jamming, because the GNSS signal, the receiver's power of the GNSS signal is 1,000 below of the ambient noise. It means that it's very weak. I mean, view the GNSS spectrum in the oscilloscope, you can see nothing, only the ambient noise. So it's very easy to be interfered. And also the signal spoofing, as I already showed you, because we do not have any state verify the signal is authentic or not. And also that is cybersecurity threat, because you see, as you see here, yes, all of the techniques we use here, we use the radio links. Radio links. It means that the radio links, maybe the radio or the Ethernet, that will, cause the threat that is already in the, the cybersecurity threat. But now I will show you very short about the signal interference and jamming and the spoofing. And here is the data got from the GWS jam. You can easy to see on the website. GWS jam, of course, the data from the GWS jam is not. I think it's not be already confirmed or not. But the data is provide us the global view of how the GNSS jamming in the global. And you can see in the area where we have the conflict, is there a lot of the interference. You see in the north of the Asia, and also in the East Asia, you can see. Yes, East Asia. And also there you can see visit the website to see the jam. The problem is that the GNSS jammer is very cheap now. It's very cheap now. You can easily to buy on the eBay. Of course, this one is prohibited to sell, because that in jam not only the GNSS signal, but also the other the telecommunications system. But it's still sell on the eBay and the Amazon by the. Of course, sometimes they do not give the exactly names of the GNSS jammer. They can give the different names. But it's very easy to buy on the markets. And you can see if we turn on the device, that will sweep all of the band of the GNSS signal. For example, in this case, the band of the GNSS L1. You can see the all of the band 24 megahertz is already the jam. So we cannot get the signal anymore. And you can see if we open the jamming you can see with the 10 megawatt, that can 10 megahertz that can block the signal, the GNSS signal up to 10 kilometer of acquisition. You can see 10 megawatt is very small power, but the affected area is very huge. That is a very big problem. And another problem that also is very, that will raise a very huge impact to the receiver. That is spoofing. Spoofing is not it's unlike the jamming. The spoofing when the device still gets the spoofing and also the authentic signal, but the spoofing signal is much higher than the authentic. So the GNSS receiver will check spoofing signal instead of the authentic. That is the problem. So the victim will follow the signal from the spoofer. Okay, thank you. Yes, and for the mitigation techniques, we have many techniques, but I can summary in the slide. First, that easiest to use, that we can use the antenna array processing, but this one is quite cumbersome for setup. And also we can see some techniques in the front end or signal condition. For example, if we can detect any abnormal in the received signal. For example, if we look up the spectrum, or you can look up the acquisition result to see any abnormal in that state. Okay, and also using the correlator and the PVT using RAM on. And now I think this afternoon the JAXA will show another solution. This one, I think, that can be used for mass receiver with the cheap, I mean, the low cost. That is using authenticated ZNS signal. So it means that the KZN will transmit, besides the navigation message, that will transmit the the navigation authentication message. We can use the navigation authentication message to verify whether the signal we receive that is already, that is correct one or not. But the problem is also have the problem because, for example, the QSNS will transmit the GPS, the ZNS navigation authentication message in L6 band. So maybe that only apply for the new ZNS receiver, not for the current one. So yes, if we want to give the navigation, the interference mitigation, you have to use a traditional one if you want to use for the current device. So okay, last one, that is some recent study in Navicenter. In Navicenter, we already provide the solution for checking the jamming, not checking, the detection. We're basing the abnormal of the spectrum and also the acquisition result. Yes, you can see we have the continuous wave interference that's so in the spectrum. This one is the supportable one. That means we implement the solution in the mobile phone combined with the front end. This one, the front end will convert from the IF signal to the digitalized signal, and then we will do the remaining state in the mobile phone. And also another solution, we're using the dual front ends, the dual receiver for spoofing detection. And the solution is very simple. We based on if the signal from the authentic signal that will be from the different satellite is in geometry will be with the different angle. But we transmit the signal from the same source. So the arrival angle will be the same. So that is the main, the main idea of our solution. That we already published the solution in the latest publication this month. Okay, thank you so much.
Thank you, Dr. Thuan, for your presentations. Exactly in 15 minutes. Okay. So I think we still have time for one questions if you have. Yes.
Thank you very much for great presentations. Can the jammers or spoofers jam or spoof you?
You make sword and shield.
Yeah.
Yeah.
Are you prepared for that?
Prepared for you?
That to protect your system from the jammers and spoofers itself. The Navism itself.
Yeah. Yes, of course. As I told you, the Navisim, our product that can be considered as a symbiotic the spoofer. So of course, in some our research, we're using our simulator for conducting the experiments and to see of course it can spoof that can spoof the normal device. But we already create the simulator, so we know how the simulator works.
So your simulator is safe from that.
Yes.
Okay, thank you.
Okay, thank you. So I would like to invite the next speaker, Dr. Lê Huy Minh, with his presentation about the characteristic of ionospheric layers that may affect the quality of the internet signal. We also have 15 minutes for the presentation and questions, so keep in mind that. you show the slides on the display? Okay. Okay.
Thank you, Mr. Chairman. Good morning, everybody. I would like to present to you some reason about the application in GPET in atmospheric study using their this is the reason of basic research in our institute. I came from Institute of Physics in Vietnam Academy of Science and Technology.
Can you use microphone?
Presentation
Excuse
is-
me, can you use a microphone? Microphone. Yeah. You can take it out. Take it out. Or you can, no? Yeah, you can sit, I think, if you cannot take it out, so that we can hear.
This is outline of my presentation. The first one, I will tell somewhat about the continuous diversification network in Vietnam and its recent region. And then I would like to present to you the method for calculation of the DSC, atmospheric total electron using GBA data. And then I would like to present to you about the calculation of the crest of the equatorial ionization anomaly and the atmospheric irregularity over Southeast Asia. And last is some main remarks. Now, I slide show you the continuous station in Vietnam and its station in Vietnam from 2005 in cooperation with the National Center for Scientific Research, a French Winston Free Station in Ho Chi Minh City here, and Huế here, and Viet in Hanoi here. And in 2009, in cooperation with the National Taiwan University, we installed 6 space stations in northwest of Vietnam for monitoring the earthquake in this region. And in 2011, we installed V station in the seismological network of Vietnam. And 2014, in cooperation with JAXA, we installed the Dallas station here, Dallas. And in 2015, we installed a station in Bạc Liêu in this equatorial observatory. And since 2018, in cooperation with Institute of Earth Science, Silica, Taiwan, we installed 10 stations in from Lan to Quan Hoa here across the Red River Fall in the north of Vietnam. And in our study, we use also some station, IGS station, as a Chiang Mai station, CUS space station, and Chu Phong station from Thailand. And MSG here in Malaysia, Batut in Singapore, Bako and Zokchu in Indonesia, and Smith in Australia. The chain, the station nearly along the longitude 105. In this slide, show you also the magnetic equator. Yes. Now, we present a method to calculate a slant DSC and use in this equation the problem to calculate the SDSC from flow-rate measurement. Yes. Yes, yes, flow-rate measured by GPS in this question. And from carrier phase measurement, yes, similar also. L1 and L2 years, carrier phase observation. Yes, also constant. And we use some computation technique applied to calculate this constant and to calculate the absolute SDSC. And then STSC in convert to vertical TSC according to the single label of Globusa. And then we can calculate also the rate of change of TSC, rate and or rate of TSC ditch, rho T. This is the ditch for studying the anospheric irregularity in this formula. In fact, rho T is a standard deviation of the rate over a 5-minute period. Here, let's show you the TSC on 15 March 2015 computed by using pulsar measurement in this figure. And in here, using combination of the carry phase and the measurement at 40, the same days on 15 March. This is better, that's calculated by this method. It's better. I use it for calculate TC in the Southeast Asia region. This last show you the satellite footprint on the subonosphere observed by GPS observed in the Southeast Asian region on April 12, 2006. Yes, so you can use the fabric to create a TSC map of Southeast Asia region. This slide shows you the Thai and latitude TSC map in 29 April 2012 obtained from Sweat in Vietnam and Association region. You see clearly the structure of the so-called equatorial ionization anomaly in Southeast Asia. It consists of one crest in the north and another one crest in the south, nearly symmetric with respect to magnetic equator. This crest can characterized by 3 parameters: TSC magnitude, latitude, or current times. Yes. You know this structure produced by so-called equatorial plasma fountain. On the daytime of the magnetic equator, east west electric field and north-south magnetic field produce the lift of plasma by vertical equatory. One supported to high altitude plasma diffuse. Downward along magnetic field into 2 hemispheres under the influence of the gravity and pressure gradients. This photo effect is main driver of the equatorial ionization anomaly. Now, in slide show you the day-to variation of the northern and southern crest parameter. And here's TSC magnitude, and here's crest latitude, and here's occurrence time from 2008 to 2023. It's November this year. Now we study the slope of these variations in 3 parameters. The first one, slide show you the daily mean of at 10.7 solar fluid index here, and daily TSC at the crest here, and red lines is for southern and blue lines for northern crest. You see there's a very good correlation between F10.7 and TSC amplitude. The correlation coefficient are 1.85 for the northern crest and 0.83 for southern crest. This means that the solar fluid is the main driver for TSC various magnitude. But now we study this correlation in detail by analysis, spectrum analysis. Here I show you the spectral of daily mean solar average F10.7. You see here some period in this parallelogram. 11 years, yes. The largest spectral amplitude, and T.8 years, yes, is harmonic up 11 years. And to 29.5 months is the preview oscillation, and here 27 days. In this from 115 days to 500 days, the spectra are very complicated. You see also the peak at 3 months and 1 year and 2 months and 3 months. That means it's very complicated. But now here, yes, yes, spectra of PSC amplitude. You see also the period 11 years, T twice 7 years, and QBO year, 1 year, and C month here, and here 15 days and 27 days. So the mean oscillation is 11 years, but we say some periods in these variations. Yes, this slide shows you spectra of altitude of air crash. We see also the period nearly 11 years here, 5.5 years here, and 3.7 years here. The harmonic this period, and QBO years, and one year here. Very big spectral amplitude, largest, and 340 days per year, and 430 days years, and one period very clearly is 15 days. Is for occurrence times. We see the similar. We see also the period of about 11 years, 4.5 years, 3.2 years in QBO, and 1 year. Yes, very big. So that is spectral amplitude, and 300 years, 400 years, days, 120 days, yeah, and 50 days. It will show you the oscillation period with the daily crash from long Chicago parallelogram. Yes, you see 50 days we offset, no offset in the F7, but we can offset in this period in the parameter of crash. In amplitude crash, latitude, yes. 27 days we can offset in the F1.7 and amplitude of crash. And 1 year Siemens we can offset in amplitude crash and everything parameter of a year and some. And 1 year also. And 11 years we can offset in F1.7 amplitude crash and latitude crash and current high of the southern crest. Now we try to separate oscillation in different periods. We use a technique. The first one, we calculate the running average of the observation data with sliding window, which corresponding to the oscillation period to be decomposed. And then we calculate the residual equal observed data, the difference between observed data and sleep data, and apply to the result of bandpass filter centered on the selected period, for example, 50 days, 27 days, 6 months, or 1 year. The bandwidth is a chosen approach to the cover the spectral peak at the desired period. Here I show you the 50-day oscillation of the aircraft parameters from 2008 to 2021. That's into PSC amplitude up to grade oscillate nearly in the same phase. In phase, it corresponds is up 0.78. It's very good correlation. And latitude occurred nearly anti-phase. Here's the correlation coefficient minus 0.82, and occurs nearly in phase with correction coefficient is 0.74. So the source of 15-day oscillation is planetary wave from troposphere. This slide shows you the 27-day oscillation of the solar plate index and 27, and TC built up area crash. Here's the 27-day oscillation at this point at 10.7 here for TC amplitude. You see the very good correlation between 27-day oscillation up at 10.7 and TC amplitude of air crash. The correlation coefficient are 0.7 for the knot and for the southern also. Here the semi-annual oscillation is good parameters up to crash. Then to create oscillation nearly in phase with correction 0.99, very good correlations. But for latitude, nearly anti-phase with the correlation coefficient minus 0.77. And for high occurrence oscillation nearly in phase also with correlation coefficient in 0.75. Now, we see the correlation, the relationship between the semi-annular up solar reach F7Z and of the TC amplitude. You see the semi-annular up solar reach. Yeah, here is the semi-annular up TC amplitude. You see the correlation between this amplitude at 10.7 and TC amplitude and 0.33. It means that the semi-annular oscillation of the TC amplitude of a crash depend not only on solar activity, but is also affected by many other factors. Yes. Here in slide show you the multi-annual index variation 2 and semi-annual oscillation of latitude area crash. And you see that version 2 is in during El Nino period. Red bars, yes, and here's by La Nina period. You see here during El Nino this period, for example, the semi-annular oscillation of the current decrease. Yes, ability of semi-oscillation of TC amplitude decrease. Right? Semi-annular oscillation of the latitude of east area crest could be influenced by lower atmosphere. This means that in the troposphere. This slide shows you also the annual oscillation of area crest parameters that for two amplitude get nearly in same phase, and for the latitude in nearly in phase aussi, for high and daily anti-phase. Yes. And what I show is yes. Yes. And now we would like to show you some reason about separate the ionospheric previous signal. Yes, this panel shows you the monthly mean at 10.7. Here's a monthly mean TC value at 2 crits. And TC value fitted by a second of polynomial at 10.7, and 6-month and 12-month period as a single suite. And here's the delta TC result after structuring the fitted it at 10.7 from northern and southern grids. Yes. Please. And would like to analyze also the spectra by using Röm's parallelogram. The delta TC variation at the grad you see also the Quibio signal in the residual. When we apply also a bus filter to separate the Quibio signal, Yeah, and shall I show you you see also the main two, and this IQ Eurospeak video. You see in here from 2010 2014 the EQO and SQO nearly in phase, but in this period nearly anti-phase. In this period nearly in phase. So during 2015 to 2000, the warm phase and the SQO was shortened, you see, and each period had 1.5 years, and people access is shortening too. So we can conclude that SQO is the main factor attracting to IQPO. And now my some recent study to ionosphere area realities. And for the data, we can give also the ROTI for each station for every years, or days. In this slide, show you the ROTI caliform data of military survey station on the 11th March 2015. So the 8-hour scintillation is the ROTI minus 0.5. And on the 12th March 2015, the 8 scintillation. And this is ROTI reaching this Wi-Fi remains the presence of ionospheric irregularity on scale of 5 kilometers or more. Here's a slide show you the day-to-day variation of the ionospheric area occurring at the Futu station. Okay. Okay. A slide shows the correlation between monthly solar fleet adequate and ROTI rate 0.5. The good correlation for the station nearly magnetic equator, yes, in for Hue and Ho Chi Minh cities. And sequence our works and the correlation between monthly mutation and SO you see before. It's a map in latitude. This was University of ROTI rate for 2012. You see almost irregular occur after sunset until midnight. Yes, it's so irregular is maximum about 2013 and 22-hour local time. A slide shows you the latitude of the secret and latitude of position where the ionospheric irregular occurrence is maximum during 2010 and 2011 period. You see the concentration of the irregular activity is about 15 degree north and 0. Yes. Near the 5 degree near the magnitude, the magnetic equator, the latitude of correct on the daytime. Yes. There's some main ones. So the first one, the CPS ratio shown near along the 105 degree longitude, includes the station in Vietnam and some one from other countries. It's very good for studies DSC version in the equatorial ionization and in the Southeast Asia region. And a very high level correlation between amplitude of threat and the daily mean solar fleet. And the longest period of that 7, so the main period of 11 years and other period that. And different period in the range of 115 and 500 days. But the diagram of the area, the correct parameter present a different period, 15 days, 27 days, 4 months, semi-annual, and even 2 years, and even year average. And FD.7 and red attribute have a largest spectrum at 11 years oscillation. Meanwhile, the southern correct attribute and azure type have the largest spectrum is the annual oscillation, and northern correct attribute has the largest spectrum in 15-day oscillations. And high evolution of equatorial ionization must be related to solar activity and many physical processes in atmosphere and also magnetosphere. And some other remarks for ionospheric reality. Thank you very much.
Thank you, Rotoming, for the presentations. I think the ionospheric study is very necessary in the NLS. So the presentation is a bit over time, so I think question for him can be made during the break time. Okay, thank you, Roto.
Thank you.
Yeah. So for the next speaker, I would like to invite Professor Ponchai Subiti from Kim Mong Kus Institute of Technologies. Professor Ponchai will present online. Ponchai?
Okay.
Okay.
Let me share the screen.
Yes.
Okay. Good morning, everyone. Can you see the screen?
Yes.
Okay. Thank you, Chairman. Okay, so I'd like to make a presentation on RFI detection and
recording in progress
and analysis around Bangkok, Thailand. So as a number of speakers have already mentioned to all of you that jamming and spoofing have become very problematic issues in today's world related to GNSS technology. So I'm not going to go through some of the early slides just to save time, as you have heard a few things already. Recently, there have been quite a few of GNSS interference issues, particularly near airports around the world. There were some events in Newark Airport registered in 2013 related to GNSS jamming. There were some drone disruption in Hong Kong in 2018. And recently, there was also GPS interference in airport in Texas and caused disruption as well. So the previous speaker has also mentioned about the GPS jam, which was one of the jamming events recording based on the ADSB technology that you can go in and take a look. You can search GPS jam and select the dates. I looked at the events 2 days ago and I saw that around this area is quite green, meaning that not much interference based on ADSB technology. But there were some few interference area. This is the west of Thailand, probably near in Myanmar region, where they have some conflicts going on. Recently, we participated with a number of organizations for the GBUS technology, ground-based augmentation system. And basically, this system is used to demonstrate how the aircraft can have the automatic landing on the runway based on GNSS technology as an alternative to the traditional ILS technology. However, the GBUS technology, which relies on the GNSS signals, it has to be validated. And in this project, which lasts from 2020 all the way to 2024, which just concluded last week with a slight delay due to the COVID reason. So because the landing system is based on GNSS technology, so there were some issues related to the gradient, ionospheric gradient delays analysis, which has to be carefully studied. And in the GBUS system, basically, the aircraft will receive the correction information from the ground station near the runway or on the runway. So with the ionospheric gradient or the spatial gradient and equal values at different locations, so airplane may receive the incorrect delay information from the airport. So that's why we had to do this study, and there was a flight test, demo test in November and December 2022. The organization include on the right-hand side, they include CAMATL, Aeronautical, the Aerotai, CAAT, and a few Japanese organizations that they're involved. On the right-hand side, on the top one, you see this the VHF antenna and also the hut where GNSS receivers are installed there. So during the experiment and also the period of study, very often the RFI observations made if you take a look at the picture on the left-hand side, KMATL is at the north part of the runway, and in the middle is the Suvarnabhumi Airport with the left runway and the right runway. On the northern side, on the left side, you see this hut. This is where the reference stations are installed. And from here, it's actually quite close to the road nearby. If you take a look on the image, you will see some lines near the hut. So these are the roads, and occasionally there are, you can see evident C/N0 reduction and fluctuation. So it has to be investigated. And interestingly enough, that during COVID-19, the GBUS experiments were also implemented as well, but there were not so many RFI events at all compared to the post-COVID-19 period. So in our lab, we decided to take a look at the RFI level analysis, comparison between the stations near the airport, which is at KMITL, and then in the city, which is at DPT9 from the Department of Planning. And we also analyzed the GNSS signals at the RUTI campus, which is on the upper right picture, as you can see here. And basically, at KMATL is more like the suburban area, but it's also near the runway, near the airport. However, for the DPT9, this is right in the middle of the city. And for RUTI, this is in another province, which is supposed to be quite more remote. And so for KMIT and RUTI, we use the Novotel receivers, while for DPT9, they use the Leica receivers. So here are some RFI level analysis. First of all, if you take a look at the top figure, these are the recorded C/N0 from DPT9 stations, which is right in the city. Okay, very, very busy. On 11 June 2023, and this figure will show the signals for different satellites, G01, 02, all the way to the G30. We only extract some of them. And as you can see that at this time, also at the bottom side, at the axis, this is epoch in second. Meaning that normally if you look at the daily C/N0, from the Rhinex file or from GNSS receiver, sometimes we don't see this type of RFI reduction at all. But if you zoom in, you start to see different level of RFI involved, or different level of reduction levels of C/N0. And for example, in 11 June 2023, you see that there are some fluctuation at 1630, at 2100 second. These are second, not time. 30, 60, and so on. And so it's quite clear that in the city, we see this type of reduction on this specific day. And if you zoom in, it's normally not so long, like about 2 minutes, maximum 6 minutes. So it means that all these vehicles they're passed very fast. At the bottom side, you see that these are the C/N0 from 3 stations. The blue one represents the one in the city, which is DPT9. Then if you look at the red one is at KMITL. Some fluctuation, but not as strong as at DPT9 for this date. And for RUTI, it's very, very clean. So the different level depends on the receiver, but we focus on the fluctuation. So from here, we try to measure the RFI levels, and in the literature, there are different methods. Here we use basically the standard deviation, and then we flip it, and then so from C/N0, it becomes the percentage of RFI. So here, we classify the RFI level of 0 to 25% as low. 25 to 50, we classify as moderate. And above 50, we classify as severe. Then we go on to make some study in June 2023 as well. And so you can see that here we compare between the station in the city, which is DPT-9, and the one at KMITL. And so the top graph is the moderate situation. So you see that for the one in the city, which is the blue area, there are cases of high moderation as well. But for both stations are quite similar. Then if we look at the severe case, it's more evident that the blue color, which stands for DPT-9, we have more cases of the severe events that occur. So how, I mean, when we classify like this, how does it really affect the real system? So here is the preliminary results of RTK performance errors during the RFI. And so here on the top graph, you see that we have the RFI in percentage as well. You know, whenever there are very big spike, then it represents some type of severe RFI levels. And then at the bottom side, here's the RTK performance at a station near KMITL. Here we use DPT-9 as the base station, and for this another station near university, this acts as a rover. So you see that for horizontal position error during these strong IFR events, there are some fluctuation as well, you know, more or less, sometimes high, sometimes low. And if you see in vertical positioning error, you see that it affects the RFI seem to coincide with these spikes in vertical positioning errors. Okay, so the next topic I would like to say is we also developed some RFI detectors based on this type of IF dongles and also mu blocks module as well. And in this project, we look at detecting power levels and detect the silver in zero. We have two versions. The first version, we detect power level, detect the silver in zero of 3 frequencies, and then we try to classify the interference status. It also has camera. It also records the spectrum during the detection, as well as the GUI, and the data are stored in database by the wireless transmission or the Wi-Fi, it doesn't matter. And then for the second version, we also detect RFI levels. We also utilize some AIs as well. So for this system, we implemented and we installed at 3 organizations in Thailand. One is at the National Institute of Metrology, and thanks to Dr. Tayatip as well, who facilitated this installation. We also installed one system at the Royal Thai Survey Department, and very recently we installed at the Suvarnabhumi Airport in collaboration with the GBUS system as well. So for this system, we record peak power, average power, and whenever there's some spikes or there's some irregular events, it will be recorded, and the spectrum will be, recorded in the clouds. And we have implemented this for a few years already. One of the issues that we also question is, can AI distinguish between types of jammers? As mentioned by the previous speakers already, that there are different types of jammers, which are so easily available but illegal in many countries. So, for example, for SMA battery jammer, if you turn it on, in this type of spectrum, that just raise the level of the spectrum. And then for the USB GPS jammer, you see different types of information, more like spikes. So here we just try to answer that if we use AI, can we separate it from these two or not? And we use the CNN, the image-based analysis. And here are some results of the confusion metrics. It looks like
Excuse me, there's no sound from your side.
Oh,
okay.
Can you hear?
It's fine
Can
now.
you hear now?
Yeah.
Okay,
it's
okay.
fine now.
Sorry.
Yeah.
Right now I'm in Cambodia. We are installing GNSS receiver at the Institute of Technology Cambodia. So I'm a little bit reluctant on the Wi-Fi issues as well. So in summary, the RFI levels really pose as a threat, right, in the city areas, as we can see that the level of RFI is much more severe. And we can record it, we can measure this type of RFI levels or analyze it using different types of instrument. So I think more studies have to be made on how this RFI affects different technology, RTK, aeronautical navigation, SBUS, and so on. And some of the software can be downloaded from our website at the Center of Excellence in GNSS and Space Weather Center as well. And I'd like to conclude my slides here. Thanks very much.
Thank you very much for Professor Bonchai for the presentations. So I think we still have time for the questions. I just have one question for you, Professor Bonchai.
Sure.
I see in your slide that you use the spectrum of the signal for image for the classifications. I wonder if you use a spectrogram with the time information or only that the photo show only the frequency characteristic.
For this part is on the frequency statistics.
So you don't use time information that can be seen in the spectrogram image?
Not in this experiment. Yeah.
Okay, thank you very much.
Sure.
Any other questions? Okay, so if so, then thank you, Professor Bonchai. We can move to the final presentations from Mr. Yoshiki Masu.
Thank you.
Yeah. Yeah. Can you have turn on the last slide from location mine? Yeah.
Okay, thank you for attending, everyone. I'm Yoshiki Matsui from Location Mind. My presentation. Oh, okay. My presentation is quite simple, so please don't worry. Yes, we have only two topics. One is the our company introduction, and second is the explanation about the one of important function in the QZSS Japanese satellite. Our company, Location Mind, is from the University of Tokyo, and we are one of the geospatial intelligence startup. We are specialized in the geospatial science, modeling for data analysis, and GNSS security. Our major customers are the large B, such like the Toyota, Docomo, NTT Data, and government such like the Japan Cabinet Office, or some project in the Ministry of Defense. And also, maybe you know, Professor Shibasaki is our CTO. Yes, today I'll explain the signal authentication. This is named as the QZNMA in the QZSS satellite. This technology can secure your GNSS positioning signals and secure your navigation. Yes, this is a simple experimental result. Spoofing can affect the location fraud from 2 to 15 minutes later after the emitting. And in the first image, we are in Tokyo, but second and third image, you can see some like strange behavior in the map. and in the fourth image, the user in Paris. It takes a time. It takes several minutes, but during that time, spoofing signal is invisible, of course, without any sounds. So the detection of spoofing is very difficult for us. On the other hand, with the signal authentication technology, the user can identify the truth GNSS signals and suspicious one. This is the very simple image for the scheme of signal authentication. The QZSS received the electronic signature for to authenticate the GNSS signal and provides to the user. User merged their public key passed from the QZSS and to the GPS, Galileo, or other satellite signals. In this image, this is for a car. But this technology is applicable for the all mobilities, such like the trucks, vessels, or drones, and all mobile receivers, such like this. Maybe you have, most of you may have. So you are involved, most of you are involved in this technology already. All right, you may know the abstract of the signal authentication technology, but how can we use it? There are some case examples. One is for the maritime industry. Many spoofing cases are found in the maritime, such like the vessel route optimization or fishing control, or sometimes the coast invasion. This is not a third-person spoofing, but self-spoofing. The owner of this ship or captains cheats their location. Such like, hey, we are in the true trajectory in the ocean coast or the ocean route, but actually they implement illegal fishing or invasion. In the conventional system, it's very hard to detect them. They are evil behaviors, but the VDES, the next generation satellite constellation system for maritime, can detect the spoofing with signal authentication technology. So the ship owners or captains cannot cheat their location. So this system can prevent them from the such illegal behaviors in the ocean. Second one is a load pricing system. This system in progress in the several Asia countries. They try to remove the gantry for their pricing, such like in the highway or other specific roads, and use the GNSS positioning signal on behalf of the gantry to price their car moving. But in this system, if user cheats their location with spoofing, self-spoofing, they can on the road, highway road, or some specific road without any fees. That can be a damage for the government or system providers. But signal authentication system can prevent their self-spoofing and cheating their road fees, and sustain the trustability of this system. This one is a more advanced one for the drone. In the near future, many numbers of drones are flying in the urban area for some usage, such like the logistics, medical support, or other delivery, or such like that. But if the drone owner cheats their drone trajectory for shorten their drone passes, or their commercial activities, it can be a risk for all people in the urban city. But collaborating with the surface people flow or car flow analysis and drone trajectory control with the signal authentication, the future drone operation can be more safely. But this is now in development between several companies in Japan, of course, including our company. But it can be a more valuable for our future society. Yes, that's it. Thank you very much for listening, and we can show some demo video in our exhibition booth. So if you are interested in our technology, please come to there. Thank you very much for.
Thank you for the presentations. So we have time for 1 or 2 questions. So just one question from me to
Sure.
make it clear. Can you go back to slide? Go back. One more. Yeah, that's it. So as I understand that, then the QGS satellite will broadcast encrypted navigation message for all satellite from the other constellation also, not only QGS, right?
Yes, exactly. This control station receive the GPS carrier or other GNSS satellite signals and make up each crypto
Okay.
electrical signature and provide the QGSS. So this scheme can be applicable for all satellites.
So the receiver will receive actually a duplicated and encrypted version of the, for example, ephemeris from the other satellite.
Yes,
and
yes.
then compare, as I understand, compare those two duplicated versions to figure out if the navigation message is spoof or not, right?
Yes, yes.
Okay.
Spoofer cannot replicate the
I
electrical
understand
signature.
that
Yes,
because you encrypted with the private key.
yes, yes.
Okay. Thank you. Any other questions?
Последняя цифра 767. Да?
Это пароль, да?
Нет, HTTPS, Zoom.
No, maybe interference. No, this is not the GNSS signal interference, but the audio
Там сотни
interference.
написано,
Okay.
какой-то кореец.
Okay. Yeah, it's time. Thank you for your attention, and our session will be finished here. Thank you very much.
Thank you.
Понятно.